I snugly nib on you.
Hi folks, thanks so much for coming to the Fungaia Science Fair. I'm so excited to tell you about my presentation. In this very exciting video, I finally get to introduce you to one of my dear friends.
REMIS, the Remarkably Efficient Mass Inoculation System. A revolution in mushroom cultivation technology. Brought to you in this free open source presentation by Fungaia, which is actually just some weird, nerdy, crusty dude on the internet.
At the heart, REMIS combines two central innovations. The first is the preparation and packaging of bulk liquid culture using sterile medical IV bags. The second is a DIY battery-powered peristaltic pump injector system that has a totally sterile fluid path. This system promises a revolution in mushroom cultivation, outpacing the efficiency and efficacy of conventional spawn production techniques by orders of magnitude. REMIS allows us to make unprecedented amounts of mushroom spawn in record time with unrivaled rates of success, reducing labor, decreasing contamination, and accelerating growth cycles. And the best part is, you can build the whole thing yourself, and I'm going to show you how.
Never give up.
In this video, I'm going to start by describing some of the bottlenecks and shortcomings of conventional mushroom spawn production methods and the problems that I set out to solve when I designed this. In the second part, I'll show you how the system works, and the rest of the video will be tutorials on how to build each of the components to create a REMIS of your own. It's been several years since I first came up with some of these ideas, and some aspects of this system I've really spent a lot of time refining, experimenting, testing, and getting dialed in. You'll see that there are other aspects of it that certainly leave room for improvement. I'm not saying it's perfect, but I've been sitting on this for too long, and I'm just really excited to see it fly the nest and take on a new life of its own out in the beautiful open source DIY mycology community, where I hope that we can all collaborate, explore its possibilities, refine the system, and share our results with each other. What you'll see me build in this video is my fourth prototype, and one of the most exciting things about this is that it actually runs on batteries. Now, I know all my haters out there are going to say this is some fake-ass mumbo-jumbo, but the system that I'm going to describe in this video can save a commercial mushroom producer thousands of dollars a month in labor and loss. So naturally, when I first started working on this idea, I wanted to turn it into a whole business of its own, make manufactured really sleek components, market everything, file tons of patents, start a huge multinational enterprise. It didn't take me long walking down that path to realize that very little of that actually aligns with my values. I would much rather keep it cheap, keep it simple, keep it DIY, and put the ideas out there for free. So I hope that you'll stick around to the end of the video to learn a little bit more about the backstory of this project and what the open source philosophy really means to me. By publishing this video, I'm effectively unpatenting this idea, releasing all commercial interest in the intellectual property, and placing it freely into the public domain. All I ask in return is that you honor the spirit of this effort by sharing this information freely as well. I certainly hope that you'll use REMIS for your commercial mushroom production operation. After all, that's specifically what it's designed for. But I do ask, without recourse, that you not commercialize the system itself without my explicit consent. Conventional mushroom cultivation techniques involve the slow, gradual expansion of mushroom mycelium, beginning by transferring wedges of agar from petri dishes into sterilized grain, then transferring that into more sterilized grain, maybe even 3 or possibly 4 consecutive times, before finally transferring the mature spawn into bags of sterilized sawdust for the final stages of growth. Not only is this process slow and inefficient, but each successive transfer compounds the risk of failure by ingress of competing microorganisms like bacteria, yeast, and mold. That's why in recent decades, throughout the entire mushroom cultivation industry, this approach has been almost ubiquitously replaced by a vastly more efficient technique, producing the same results in a fraction of the time with a fraction of the work. You may have guessed by now that I'm talking about liquid culture. Liquid culture is the product of an aerobic fermentation process. This process begins by pulverizing an entire petri dish of mycelium in a sterile nutrient broth, then fermenting it with constant agitation and lots of oxygen contact under totally sterile conditions. Within just a matter of days, the mycelium expands its biomass by several orders of magnitude, and the constant agitation breaks apart the mycelium continuously into lots of tiny free-floating clusters of cells. One single petri dish can make several liters of this liquid, and just 3 or 4 milliliters is enough to inoculate an entire kilogram of grain spawn. A quick side note here, I want to make sure to differentiate between cell slurries, spore slurries, and liquid culture. A cell slurry is where you just pulverize the mycelium in sterilized water and then use that to inoculate your grain spawn. It's much more direct, it's very quick, and in general, it's a very reliable technique, which has been a mainstay of the commercial mushroom industry for a long time. Spore slurries are really only used in hobby mushroom cultivation due to a widespread misconception about the legal status of spores versus liquid mycelium. Liquid culture, on the other hand, is mycelium that's actually been grown in the liquid broth. While the preparation of liquid culture is a little bit more involved than using spores or cell slurries, it is by far the most reliable and efficient technique for expanding fungal biomass. The liquid culture technique has utterly revolutionized the entire mushroom cultivation industry for hobbyists and commercial growers alike. By packaging liquid culture in sterile single-use syringes, it can easily be stored, shipped, and then injected into pre-sterilized jars or bags of grain spawn, thereby bypassing the need for expensive laboratory equipment or specialized sterile techniques. This has made mushroom cultivation more accessible to the general public than ever possible before. On the other end of the spectrum, in the commercial mushroom industry, liquid culture has increased production efficiency on multiple different levels. It makes for faster inoculation, and it makes for fewer spawn transfers, allowing the grower to produce as much spawn as they need to in one pass. In turn, this minimizes the exposure risk of multiple successive transfers, thereby reducing contamination rates. It's also very easy to test liquid culture for its purity and its vitality before it's put into production. Once a batch has been verified, then many bags of spawn can be made in short order. Nonetheless, inoculation and spawn transfers remain two of the major bottlenecks in commercial mushroom production, as well as two of the primary contamination vectors. This is where REMIS comes in.
Is your mycelium running? Then you'd better go catch it!
Conventional mushroom cultivation methods involve sterilizing grain or substrate in large autoclaves or retorts, and then cooling them under carefully managed sterile conditions before inoculating them using sterile technique, and then sealing them for incubation. With this system, usually the bags are opened in front of a laminar flow hood, and then the grain spawn or the liquid culture is free poured from above. Even with the surest hand, this is a time-consuming process. Regardless of your sterile techniques or equipment, anytime you have bags of perfectly prepared, sterile mushroom fodder open to the air, there's always going to be a higher risk of failure. Meanwhile, over in the very different world of do-it-yourself hobby mushroom cultivation, most growers who want to scale up simply do so by taking a process that they know works and repeating it over and over again. If it works to use one syringe to inoculate one jar of grain and transfer that into one plastic storage tub, then it should work to use 50 syringes and 50 jars and 50 tubs. From a commercial grower's perspective, this is obviously wasteful and inefficient, but it does offer the distinct advantage of compartmentalizing any possible issues, a sound insurance policy against the spread of pathogens. REMIS is essentially the hybrid offspring of both of these approaches, combining elements of each to create the most efficient possible workflow with the most consistently favorable results. The idea is that, like the home grower and her many jars, we sterilize a large amount of mushroom spawn in spawn bags and seal them right away while they're still hot before any risk of ingress.
Since I'm sealing the bags under laminar flow, I also like to draw some air into each of them first. This saves an enormous amount of trouble when it comes time to mix them later on after inoculation.
Since each of these bags has a small but very effective sterile air filter, once they're sealed, they're safe to just set on a shelf and store until they're ready to be used. Not only does this bypass the need for clean room cooling, it also allows us to run our autoclave back to back, a great advantage considering that this is usually the biggest bottleneck of all in mushroom production. Once the bags are cooled, they can be left indefinitely, the only risk being that they will eventually gradually dry out. If there's any concern at all about adequate sterilization, we can leave the bags alone for at least a few days to incubate them and see if anything grows before we waste any of our precious inoculum. Next, rather than the tedious and risky transfer of spawn manually in front of a flow hood that most commercial growers use, or the alternative of filling 100 individual syringes and using them to inoculate each bag separately, a clearly wasteful and time-consuming prospect, we'll use REMIS to efficiently and quickly inoculate as many as 100 bags in a single pass.
First, we steam sterilize the silicone tubing in the injector shaft, wrapped in aluminum foil for good measure. Then, under laminar flow, we connect the tubing to a sterile needle on one end and to the liquid culture IV bag on the other end. We now have a completely closed system. Next, we hook into REMIS, running the tubing through the peristaltic pump and clamping the injector shaft into place. Now we can begin to pump the liquid culture directly into our sterilized bags, spreading it throughout the grain or substrate. I also like to pause from time to time and install a fresh needle, just as a precaution. These are cheap and they can be re-sterilized and reused many times. One by one, we'll work our way through all the bags, using the pump reversal switch anytime we need to clear the occasional clogged needle. Once the whole run is complete, we can seal over our injection ports with an extra piece of tape for good measure, then label all the bags with the inoculation date and some strain data. I like to use thermal labels and a receipt printer so I can quickly print the precise number of labels I need. Finally, we'll mix the grain thoroughly and put it on a shelf to incubate. I find that one thorough mixing right after inoculation is usually all it takes for incredibly fast, even growth.
All right, it's been exactly a week since these were inoculated, and as you can see, they're all pretty much ready to go. Even these ones that look a little lighter, if you look, all of the grain is covered with mycelium. That's ready to spawn out. Generally speaking, with most gourmet mushrooms, you'll be able to get to full colonization in about 5 to 7 days using this technique. It's incredibly fast, and it requires significantly less work than other conventional grain spawn techniques where you're shaking jars and breaking up bags on a regular basis. This is kind of a one and done method, and for the most part, it works really, really well. This bag obviously didn't get fully mixed, so I might mix that one up today, but it's pretty close. The reason I grew out this much Oregon reishi, which I absolutely love, is actually because it's a very good candidate for mycomaterials. The strong, tenacious mycelium has high tensile strength, and as I'm going to experiment with, I believe it also has unique acoustic properties. So stay tuned if you'd like to see the rest of my experiment using this grain spawn to make some acoustic panels for my sound system studio. Now, I'll get into the specifics of the system in just a moment, but before I move on, I want to plant one more seed that I hope will really get your wheels turning. Obviously, the method I just described could be used to make a large quantity of grain spawn, which could then be spawned into bulk substrate bags using the conventional free-pour spawning technique. What I want to propose instead is a totally different workflow in which we use REMIS to inoculate our bulk substrate directly using large quantities of liquid culture and bypassing the spawning stage altogether, thereby eliminating one of the most contamination-prone, problematic, and time-consuming parts of the entire cultivation process. Once we've figured out a perfect, balanced bulk substrate recipe, we can create a ton of bags all at once, sterilize them all together, seal them, and leave them on a shelf to incubate to make sure there aren't any problems. Then, as soon as we're ready, we can inoculate dozens in a single pass. In my experience, these bags will actually take less time to incubate than a bag that's been inoculated with grain spawn. Now, if you're a commercial producer who's been relying on grain spawn for years, all of this might start to sound pretty far-fetched. There are certainly many applications in which grain spawn is still going to be the most efficient and productive method, particularly in the cultivation of compost and dung-loving mushrooms. But in the large-scale production of wood-loving mushrooms on supplemented sawdust substrates, I foresee that pretty quickly the industry is going to catch up to this line of thinking, and we'll see grain spawn go the way of the dodo. Now, as with all of my advice, I recommend you take it with a grain of salt and go investigate for yourself. I have a feeling that the results might surprise you. In any case, I hope this gives you something to chew on. For now, let's move on and talk about the nuts and bolts that really make REMIS tick. First, let's talk about liquid culture. In this part of the video, I'll cover 3 topics: how to brew large quantities of liquid culture, how to package it in medical IV bags, and how to filter it for smooth inoculation. Liquid culture has long been one of my specialties, and I developed a unique but very effective technique using a mason jar and a modified blender as a sort of DIY Eberbach stirrer to turn petri dishes into liquid culture very efficiently. I described this process in detail in my early YouTube video, How to Make Liquid Culture. That same method can be used to start numerous batches of liquid culture simultaneously or to make larger quantities. To fill a 1-liter IV bag, I like to brew in one of these 2-quart mason jars. In this case, I'll usually sterilize 2 jars, a small jar that has the blender base and part of the water, and then a large jar that has the rest of the water, all the ingredients, a stir bar, and a filter lid. I'll pulverize the mycelium in the smaller jar and then pour that cell slurry into the larger jar for the fermentation. Alternatively, you can cut up agar wedges manually and transfer them into the jar one at a time, or even inoculate your sterile nutrient broth using a liquid culture syringe. In theory, you could make as much culture at once as you have the vessels and equipment to adequately sterilize and operate. From mason jars to brewers' carboys to industrial bioreactors. In fact, this is the same process that large manufacturing laboratories use to produce industrial quantities of things like citric acid and other products of specialized fermentation. Scaling the production of liquid culture is one thing, relatively straightforward, but it presents additional challenges when trying to transport, store, and dispense it. For small amounts of liquid culture, nothing can really beat the simplicity, reliability, and ease of using sterile single-use syringes. But fond as I am of syringes for small-scale and home cultivation, they're just not practical for large-scale production. Filling hundreds of plastic tubes for them to be quickly emptied and then discarded is, of course, very inefficient and a terrible waste. This is why, early on in my journey as a producer of bulk liquid culture, I began exploring the use of sterile medical IV bags. Around the lab, I simply use jars to store all of my liquid culture. If you're keeping all of your production in-house and you're doing all of your transfers in front of a laminar flow hood, you can just use REMIS to pump straight out of your jars. But if you want to ship the liquid culture, or you want to be able to inoculate outside of the sterile environment, maybe do your inoculations in the incubation room, jars are problematic. For one thing, with glass, there's always a risk of breakage. But the biggest problem with jars is that every time you're drawing fresh air into the environment, you're reintroducing oxygen. And this becomes problematic, especially when you want to reuse culture or keep it in cold storage. After the liquid culture has been fermented, when you package it in the absence of oxygen and keep it in cold storage, it will go into a state of dormancy that it can maintain for a very, very long time. This is part of what makes liquid culture so resilient and so reliable. Syringes prevent oxygen contact as you push the plunger in each time you use it. So, following the same logic, IV bags are an obvious choice. They never leak, and, most importantly of all, they prevent any oxygen contact. If they're sterile enough to pump stuff into someone's blood, they're probably sterile enough to use in mushroom cultivation. Honestly, the biggest problem I've had with the IV bags is finding someone who will sell them to some crusty kid with no medical license. So as a courtesy, I'll be offering sterile medical IV bags on my website at fungaia.life/remis. So, we have some liquid culture, and now we have a sterile vessel to put it in. The next trick is moving it from one to the next, cleanly and efficiently. There's quite a variety of different sterile fluid transfer systems, but they aren't easily mixed and matched, and it's not always obvious or easy to find information about these systems.
First of all, I use silicone tubing for all fluid transfers. It's easy to work with, and it can be steam sterilized before each use. It's also a necessary part of working with a peristaltic pump, which I'll discuss more in just a moment. I also really like to have a pair of locking forceps, which I can use to pinch off the tubing at any point to stop the flow of liquid. I use lure lock adapters to make all of the tubing connections, and I modify plastic jar lids to make dip tubes for drawing culture from my jars. All of these parts are made of polypropylene or silicone, which can handle the heat of the autoclave or pressure cooker. I also replace them periodically, just for peace of mind. In the open source spirit, I've made a comprehensive list of the IV bags, fluid transfer supplies, and all these different fittings on the REMIS page on my website, with links so you can go find them yourself. I also stock a few of these items and put together a couple of kits for purchase if you'd prefer to save yourself the hassle of searching, while also helping to support the future of Fungaia.
Almost all of these bags come with an injection port used for injecting syringes of medication to mix for an IV drip. Using the injection port is probably the path of least resistance, so to speak, for most people who are only dabbling with 1 or 2 bags at a time. I always ship my IV bags with a large syringe and several extra needles for this reason. But pumping through tiny needles over and over again is painstakingly slow, plus going into an injection port over and over isn't ideal either. Liquid culture is also often very chunky, which causes a lot of headaches with clogging needles. I'll address this issue shortly. Probably the most familiar and accessible sterile fluid transfer system for us mushroom nerds is the lure lock system, which we all know well from working with syringes. Lure lock fittings are standardized and relatively easy to find, and they're almost always made out of an autoclavable material like polypropylene. Lure lock connectors consist of a male end and a female end, which are both slightly tapered to create lots of surface contact. Lure lock fittings, unlike lure slip fittings, also include threads that allow you to tighten that tapered connection to make sure that it won't slip or leak. I was never able to find IV bags that come with lure lock fittings already attached, but with a little trial and error, I figured out a good system for connecting my own adapters.
First, I snap off the fill tube cap. Under the cap, the fill tube also has a membrane that's sealing it, which has to be punctured. For this, I whittled down and sterilized a little prison shiv. I make sure to work it around a bit to really open up that membrane. These bags are made of some crazy medical technology self-healing material, and if I don't keep the fill tube membrane forced open, it'll seal itself right shut again. So, I'll use a 3/16 lure lock adapter and push it in far enough that it actually holds the membrane open. If you're doing dozens of these bags at a time, it can start to hurt after a while, so I went ahead and modified a pair of pliers to make it easier. Once installed, this adapter allows me to easily connect and disconnect the fill tube. I always install it with a cap. Then, if I'm going to be going in and out of it multiple times, I'll also install a valve called a stopcock with lure lock fittings on each end. Among other things, this will allow me to easily fill syringes from the bag. For best results, all of this must be performed with impeccable sterile technique in front of a laminar flow hood.
Next, we'll need a pump. As I'll describe in the next chapter of this video, this is most easily achieved with a peristaltic pump. They can be fairly expensive to buy, but they're not hard to build on your own. And of course, I'll show you how in this video with lots of detailed instructions. But if you're not ready to commit to that, I'll also show you how to make a simple mechanical manual pump using just a syringe and a couple of one-way valves.
The valves are just cheap plastic check valves. You'll also need lure lock fittings for each of the 3 connections and a T in the center. All of these parts can be sterilized together in a pressure cooker. I like to wrap them all in aluminum foil, which helps keep everything together and makes them easy to handle after sterilization. I also wrap the tips in foil separately, reducing the chance of contact with potential contaminants, since these are the only parts that are actually coming in direct contact with the liquid culture. This makes it easy to connect the system one side at a time. With one end connected to the liquid culture vessel and the other to the bag, we can steadily draw liquid into the syringe from one side and then push it out the other. All it takes is a few slow, steady pumps, and all the culture is safely transferred. With this setup, it's very important to quickly and thoroughly clean the parts after use so nothing grows inside the tubing or valves. The plastic fittings do degrade eventually, but I've found that as long as they're kept clean, one of these pumps can be re-sterilized and reused many times. I stick the inlet tube into a jar of clean water and flush it by pumping it a few times. Then, I pump plenty of air through it to blow all that extra water out. Then I'll pop the plunger out so the whole thing can air dry. I also offer these pumps pre-assembled on my website for your convenience.
Now, before we move on to the really juicy stuff and talking about peristaltic pumps, there's one more issue I want to address, and that is filtering. As mycelium grows in liquid culture, it's not uncommon for it to form dense chunks, and if you inoculated it in the first place using agar wedges, clogged needles during inoculation can become a real nuisance. That's why I always filter my liquid culture before inoculation. Now, it's not an absolutely necessary step, and it does have the downside of removing some of that precious mycelium. But I find that it's very much worth the trouble, especially considering how much smoother that next step will be. We don't need to filter it like crazy, just a coarse filter mesh will usually do the trick, just to remove the large chunks that would otherwise clog those 16-gauge cattle needles that we use for inoculation. One way to filter the culture is simply to pour it through a sterilized stainless steel kitchen strainer in front of a laminar flow hood. For this, I'll use a stainless steel canning funnel and 2 strainers stacked on top of each other, which speeds things along and reduces exposure time. I wrap the whole thing in aluminum foil when I sterilize it to make it easier to handle. This process is obviously risky and requires excellent HEPA filtration. Overall, I've had excellent results with this technique. Nonetheless, I've always wanted to figure out a better way that reduces exposure risk and streamlines the process. I've played around with syringe filters, I've tried making my own plastic inline filters with various polypropylene fittings and containers, and I've spent some time looking into solutions developed for other industries like pharmaceuticals, dairy, and wine. Over time, after lots of experimentation, I eventually developed my own inline filters that use modified tri-clamp fittings and some silicone tubing. Obviously very overbuilt, but they definitely work. Originally developed for the dairy industry, these sanitary fittings can create exceptionally strong fluid transfer connections. They tolerate high heat, massive amounts of pressure, and allow everything to be kept sterile, which has made them very popular for many other industries as well, particularly beer and wine. My custom inline stainless steel filters have a hose barb adapter on either end that I can connect my silicone tubing to. They use a high heat resistant silicone gasket, and then I've just TIG welded a pipe nipple on there that allows me to connect this brewing kettle stainless steel mesh tube. The precious liquid culture, which passes in this side, has to be forced through the stainless steel mesh in order to come out the other end. It provides plenty of surface area to filter a large amount of mycelium without clogging.
Just like the rest of the transfer system, I wrap the ends of the tubing in aluminum foil to keep them clean for safe handling after sterilization. Then I cook the whole setup in the pressure cooker along with anything else I might need. I make sure to allow the steel to cool under laminar flow, and then I'll connect the filter inline between the culture jar and the IV bag. I begin by charging the filter, pumping the culture in until the whole filter housing is full and all the air has been pushed out. Then I can connect the IV bag and start the actual transfer. Then I'll switch the pump to the other side of the filter and hold it upright to drain all of the remaining liquid culture out of it. Finally, I'll clamp the line with my forceps, disconnect the pump, and then release any air that's trapped in the bag before I cap it off, parafilm it heavily, and send it on to the inoculation line. I also always make sure to save a few drops in the line that I can drip out onto a petri dish to do a streak test and make sure that my culture is clean.
A full 1 liter bag of liquid culture is an immensely satisfying object, like a dragon's egg, brimming with possibility. Once it's filled, capped, and sealed with a bit of parafilm for good measure, it's ready to head out of the lab and into the grow room, or perhaps into the fridge for a while, or maybe even into the mail, where it'll find a new home. Hopefully, this video provides you all the information you need to go ahead and make some of these yourself. But of course, you can save yourself that learning curve by ordering some of these from me. I produce these bags on a custom order basis with about a 3-week lead time depending on the variety selected, and they're available for purchase right in my shop at fungaia.life. And if you're in the market for top-tier liquid culture and you're looking for a wider selection of mushroom genetics, make sure to check out our friends and sponsors True Blue Genetics at truebluegenetics.org. Not only are they one of the absolute best sources for clean, vigorous liquid culture syringes, but they also offer custom order 1 liter bulk IV bags of liquid culture of anything in their incredible library. All of it's totally compatible with REMIS and backed by a sterility guarantee. Make sure to use the coupon code REMIS for an extra 20% off and to let them know that we sent you. Not only will you get great genetics at a great price, but it goes a long way to help support the creation of more fun, free educational videos like this one.
I snuggling in you.
As you've no doubt gathered at this point, the beating heart of REMIS is the Peristaltic pump. Next up, I'm going to tell you a little bit about what they are and how they work, and what to look for if you're going to go out and buy one. Then, I'll walk you through a detailed tutorial of how to build your own battery-powered Peristaltic pump injector system. Like squeezing out some toothpaste or moving food through our digestive system, pushing fluid through a tube by way of wave-like contractions is called peristalsis. A peristaltic pump moves fluid through a tube by continuously squishing it using a series of rollers that are spinning, driven by a motor. Peristaltic pumps are quite slow and not very efficient, but they do offer some special advantages. For one thing, the amount of fluid transferred, assuming a consistent density, is directly proportional to the number of rotations of the motor, allowing for very controlled, precise volumetric measurements. Peristaltic pumps can also operate under pressure and under vacuum. But, most importantly for our application, peristaltic pumps can make completely sterile fluid transfers by maintaining a sterile fluid path. This is because the fluid never comes in direct contact with any of the moving parts of the pump. The tubing itself is independent of the pump, allowing it to be attached, used, and disconnected easily without ever disconnecting the tubing ends. This means that we can sterilize the tubing and all of the fittings together, assemble a whole closed fluid transfer system, and then connect it to the pump and begin the transfer process. Given these specific advantages, peristaltic pumps are most often encountered in the medical industry, where they can be used to continuously titrate medications on a programmable cycle, or in organic chemistry, where they could be used for mixing solutions without operator exposure. Now, there are some cheap consumer-grade peristaltic pumps out there, and some of them may work for mushroom cultivation, but it's important to make sure that you get one that allows for quick tubing changes and has a sort of clamping mechanism on the pump head like this. On the other end of the spectrum, there are great options for some powerful, fully programmable dosing pumps. The downside, however, is cost. In many cases, they come with a 4-figure price tag, which generally puts them well out of reach for most scrappy mushroom farmers. But I say, why shell out a bunch of cash when, with just a little bit of solder and plenty of hot glue, you can make your very own, totally programmable, functional peristaltic dosing pump? Next up, I'll show you how to do just that. Plus, you're going to get to see how to add 2 features that you're not likely to find anywhere else. How to install a lithium-ion battery pack so that you can take your REMIS on the go, and how to build the custom injector that'll allow you to control your dosing remotely. First, I'll tell you about all the supplies and parts that you need, which you can also find in a complete list on my website at fungaia.life/REMIS. This way, you can make sure that all the parts you get are compatible and are going to work the same way that they do here on this video. Initially, my goal in building this system was to create some kind of marketable product for commercial mushroom producers. I was trying to create an interface that had a nice LCD screen and would allow you to set dosing parameters and control the pump speed and that kind of a thing. But frankly, I'd rather spend my time making these videos, hanging out here with you, than tinkering with some gadget endlessly. Suffice it to say, this is the 4th version that I've built, and they've certainly improved throughout the iterations, and there's also certainly a lot more room for improvement. Take everything I'm saying in this build with a grain of salt. I just really wanted to kind of get this out there. I'm tired of sitting on this idea. I hope you'll build one of your own, and I hope that you'll improve the design and share your improvements with me and with others. Ready? Let's head to the shop. All right, let's talk about our parts and supplies. Now, this tutorial assumes that you already have some working knowledge of electrical systems and at least a basic soldering setup. For this, I recommend a soldering iron. You're going to need some rosin core solder. I love to use a hot glue gun. For a lot of my electrical work, you'll need some wire strippers, a heat gun, and some heat shrink. For everything we'll be doing, 20 gauge is probably big enough, but I recommend just getting some good all-around 18 gauge electrical wire. It's a great size to have on hand. You'll also find it really handy to have a benchtop power supply and at least a basic multimeter for this, for testing continuity and that sort of thing. Now, as for the parts themselves, there are 4 primary components that'll make this work. The first is the pump head, which usually comes attached to a stepper motor. You'll need a driver that can power that stepper motor, and then you'll also need a PWM signal generator, which will help you control the speed of the motor rotation. Now, if you're someone who likes to reinvent the wheel, you can certainly build your own pump head from scratch, but it's a fairly complicated and precise tool, so I think it's worth just getting a factory-made peristaltic pump head, and make sure to get one that allows for quick tubing changes. That'll be important. Next, you'll need a motor. Now, most peristaltic pump heads will come with the motor already attached that's size to that pump. Specifically, we want a stepper motor. A stepper motor is a special type of motor which is digitally controlled to progress through a series of steps rather than rotating continuously. They can move forward and backward and allow for a high degree of control over speed, torque, and rotor position, making them the perfect tool for a lot of applications where a high degree of control is needed, such as CNC routers, 3D printers, and that sort of thing. Stepper motors are perfect for peristaltic pumps because they can produce high torque at low rotational speeds without using a gearbox, which is important when we're squishing a tube over and over again, but don't want to do it too quickly. It's also very important to get a powerful enough motor to drive your chosen pump head, which is why they're usually sold as a set. The most common choice is usually a NEMA 17, or if you want to really overpower it, you could go with a NEMA 23 stepper motor. In order to properly install a stepper motor, it's important to understand how they work. Stepper motors function by fluctuating power between 2 independently powered electromagnetic coils, which are offset at different nodes. By powering one coil and turning off another, the motor will progress to the next step in the sequence, and when this is done in a continuous fashion, it creates what appears to be a fluid rotating motion. Most stepper motors have 200 steps per rotation, but we can also partially power the different coils to get the motor to land somewhere in between the two, which allows us to exponentially increase both the amount of control and also to increase torque. This is called microstepping. All of this control is generated using a stepper motor driver. We connect the input power to the driver, and then the driver sends that current to the motor, fluctuating it between those different nodes, and allows us to set our microstepping ratio, and allows us to determine the speed of rotation using an input control signal, which we generate using a PWM signal generator. PWM stands for Pull My Wanker. PWM stands for Pulse Width Modulation, and it's just a simple way of sending a control signal. Normally, this would be sent by a computer or a microcontroller, as in the case of, say, 3D printing, where we want to assign very specific motions to our stepper motor. In our case, we can do it a lot simpler. These are off-the-shelf parts. You can get these for about $2 a piece. I like this. It's got a little bit more of a sophisticated interface. The pulse width, which is essentially the on-off ratio of our control signal, is called the duty cycle. For a stepper motor, we'll keep the duty cycle at an even 50%, meaning it's on and off 50% of the time. The speed is actually determined by the frequency of that signal. Each time our signal generator sends a pulse to the motor driver advances our stepper motor by 1 step, or by 1 microstep if we have that set. Once the whole system is assembled, it'll be relatively easy to determine the correct operating frequency for your stepper motor. Obviously, we want to transfer the fluid as quickly as we can. Higher frequencies mean higher RPMs, and that means higher fluid transfer rates. However, the higher your RPM, the lower your torque, meaning that if we crank it up too high, the motor will actually stall and won't be able to push the fluid at all. We can increase the torque by adjusting our microstepping ratio. The finer our microstepping, the higher the torque, but also the slower the max RPM. In addition to these primary components, you're also going to need to have a handful of other supplies. You'll need a power supply that's sized to your stepper motor and your battery pack if you're going that route. I always like to have input DC power jack with some fuse protection on it. You're also going to need some switches. Obviously, you'll want one as your primary power switch, but if you're going to build the injector pump that I described here, you're also going to want to be able to manually switch between the injector mode and just manually turning the pump on. For that, you'll need an on-on 3-prong toggle switch. You'll also see me install a third toggle that allows me to reverse the pump direction. This is really helpful with clearing clogs, and it's also just nice to be able to decide on the fly which side you want to have your inlet and outlet on. If you want to build the injector system that I show in this video, you're also going to need some sort of trigger for that, just a momentary push button toggle, and some way to send the signal from that to your stepper motor driver. For this, I use just standard 3.5mm audio cable. The injector also relies on one of these stainless steel lure lock extenders. The other big innovation here is that you can run this whole system off of a lithium battery pack. Not only is this going to help you create an uncluttered, sterile workspace when you're using the pump, but it also means you can take REMIS on a walk with you through your inoculation room. For that, you're going to need some batteries and a BMS, and I'll talk more about that in that section of the video. Again, you can find a list of all of these parts with the detailed information on my website at fungaia.life/REMIS.
The first step is to build a box. I made a mock-up and measured all the components to first determine my box dimensions. I'm going to make this one 4 by 4 by 7.5 inches. For the ends of the box, I'll use some scrap 3/4 inch plywood. This is pre-finished maple, which will hopefully help make the pump easy to clean and sanitize. I'll cut the base out of a couple layers of thin 5mm plywood and glue them together. Together, these will make the chassis of the pump. Before I glue them together, I'll trace out the stepper motor and make a cutout for it to easily slide through. Next, I'll give the corners and edges a quick round over on a router, as I'm always in favor of cutting corners. Rather than build the whole thing out of wood, I thought I might try a metal finish. This is just some aluminum roof flashing I had lying around. I pre-drill all my screw holes to avoid splitting the plywood, and I'll use some panhead lath screws to hold the metal in place. Next, I'll mark and cut the holes for the PWM signal generator, the 3 toggle switches, the power jack, and the headphone jack for the injector. Now I'm ready to start assembling the components. First, I'll put in the pump head. Normally, it might be easiest to use some bolts or brackets or something to hold it in place, but I want only the finest for my REMIS, so I'm going to upgrade to using a generous amount of hot glue. The next step is to wire the stepper motor into the driver. I've learned the hard way that different motors have different wire colors, so you can't necessarily just copy my homework on this one. The stepper motor has 2 different coils, which correspond to A and B on the driver. Thankfully, polarity doesn't matter here, and A and B are interchangeable. We could do a simple continuity test using a multimeter to figure out which pair of wires corresponds to each coil. Once you've determined a pair of wires that have continuity, you can wire these into the A negative and A positive terminals on the driver. Using advanced deductive reasoning, we can determine that the remaining 2 wires fit into the other 2 terminals. Once all 4 wires are firmly connected, I'll mount the motor driver just behind the motor, leaving enough room for heat dissipation. Different motor drivers may not have this feature, but mine has a switch panel and a code printed on the face that allows me to select different output currents and microstepping ratios. Based on the specifications of my motor, I'm going to set it to 1.5 amps. Based on my experience, full step control stalls too easily, so I'm going to go with a 1/2 step ratio, which I think is an ideal balance between power and pump speed. The next thing I do is install the power jack. This is the main power inlet, so this is where I want to put my fuse protection. I'm actually connecting 2 different electrical circuits through this one point. One runs the pump, and the other connects the battery pack. So I'm going to use a separate fuse for each one. The size of the fuses is determined by the power draw of the motor, which is less than 2 amps, and the output of the battery charger is 4 amps. In this case, I'll use a 3 amp fuse for the motor and a 5 amp fuse for the battery pack. All wiring and components must be rated for at least 5 amps of current, though I always err on the side of caution and oversize my wiring. After that, I'm ready to install the audio-style jack for the injector switch. Next, I'm ready to start wiring in my toggle switches. The first toggle will be my main power switch, which connects the positive coming in from the fuse holder to the positive terminals on the PWM and on the motor driver. The second of the 3 toggles switches between injector control and manual control. This is a 3-way on-on toggle that carries the output signal from the PWM to the motor driver. This is the signal that tells the driver to turn the pump. So one side of the toggle simply turns the pump on. The other side of the toggle passes the signal through the injector jack. With the toggle in injector mode, the pump will only turn on while the trigger is pressed. The third toggle reverses the pump direction. I actually wired this wrong. In my first iteration, I simply connected the switch directly to the motor driver DIR pinout, but this didn't work. Skipping ahead a bit, I'll show you how I fixed it. First, instead of looking this up, I tried to figure it out through experimentation and ended up accidentally frying the direction input on the driver. Unfortunately, this meant that I had to replace the whole stepper motor driver, though thankfully this was very easy. Then, I had to do some research, like I should have in the first place. Now I understand that the step and DIR pins on the driver actually require a higher low digital logic signal to function, which are typically supplied by a computer or a microcontroller, as in the case of a 3D printer or a CNC router. I figured out that it actually works totally fine to simply use the output signal from the PWM generator. Regardless of the frequency of the signal, the motor driver will register this as a high logic signal and the pump direction will be effectively reversed. I found that pump direction reversal is absolutely crucial, especially for clearing clogged needles. So I was glad I managed to get this working. Okay, now, going back. After the toggles are soldered in, I'll wire in the PWM signal generator. The one I'm using is rated to 30 volts, so I can just wire it directly into my main 24 volt input power. Make sure to check though, because not all PWM units are rated to that high of a voltage. The output from the PWM signal generator then connects to the step terminals on the motor driver. Now, I'll hot glue everything into place, including the power and injector jacks. And that's it. We have a perfectly functional peristaltic pump. If you're going to skip the battery pack and the injector system and just build a basic pump, then this is all you actually need. Otherwise, let's start on that battery pack. For this build, I'll be using top-of-the-line Molicell P42A, a 21700 cell rated to 4000 milliamp hours. But any old 18650 will do. I'm going to use 7 of them in series, which have a functional voltage range of 21 to 29.4 volts, which is perfect for running our nominal 24 volt motor. The battery pack is an incredibly cool feature of REMIS. But if you're going to go this route, I beseech you to do a little research and make sure that you really understand what you're doing before you just start soldering lithium cells together. Lithium batteries have a higher energy density than TNT and can be extremely dangerous. If you short circuit them, they begin rapidly producing heat. The hotter they get, the more power they release. This can lead to something called thermal runaway, which results in very hot fires that are nearly impossible to extinguish. Not to fear though. This is a small pack, and the low amperages and a good dose of common sense will keep us out of trouble. The main thing is that we always only want to use lithium batteries in conjunction with a battery management system called a BMS. This very handy little circuit board will allow us to safely charge and discharge our battery pack and offers a variety of optimization and safety features such as overcurrent, overdischarge, and temperature protection. The BMS must be specifically designed for the number of batteries and their recording voltage. Any BMS worth its spit will also have a number of separate leads that allows it to monitor the voltage of each individual cell in the series. Not only does this prevent catastrophic damage, it allows for charge balancing. Throughout many charge cycles, the batteries will eventually start to charge and discharge at different rates. The BMS uses the balancing leads to discharge each cell slightly once it reaches full charge, bringing all the cells back to the same exact voltage if they start to wander. It helps a lot to hot glue the batteries together to make a solid pack before soldering them. You'll also see me use some nickel strip to connect the cells, and I find that a very light sanding of the terminals and some lead-based solder make the soldering a lot more manageable. First, I apply a dab of solder to each of the battery terminals and the ends of the nickel strip. Then, I press the two together until the solder melts and merges. I take great care to solder my battery pack in the correct order, double checking my work at every turn. I'm also very mindful of my tools, making sure that I don't accidentally short any of the cells. I proceed through the series, using the nickel strip to connect the positive terminal of the first battery to the negative terminal of the next, and so on in the exact order through to the 7th battery. Then I'll wire in the BMS, starting by connecting it to the negative terminal of my first battery. Proceeding through the series, I'll wire each of the skinny leads in order to the junction between the positive terminal of one and the negative terminal of the next. By the end, I should be soldering the final balance lead onto the positive terminal of my 7th battery cell. Depending on your type of BMS, you probably don't have a positive wire coming off of it. Mine has 2 negative terminals, one to connect to the ground circuit on the device, and the other to connect to the batteries. The positive lead just gets soldered to the positive terminal of the final cell in the series. Finally, I'll solder the negative to the ground wire on the power jack. Before I do anything else, I like to double check my work using a multimeter. I'll work through the entire battery series, testing the voltage between that first negative battery terminal and each successive positive terminal. Each cell should climb in voltage by a consistent increment of around 3.5 volts, depending on the charge status of the cells. Now for my favorite part of the battery process. Using some specialized heat shrink to wrap the whole pack for that finished, I didn't just hot glue and solder this in my garage kind of a look. At this point, the whole circuit is live. I can hot glue that battery pack into place, and then close up the whole unit and begin testing and even using the pump. To complete our REMIS, the last step is to build the injector. For this, I'll use some more of that scrap 3/4 inch plywood and trace out something like one of those phasers from Star Trek. I'll cut this with a jigsaw, and then I'll trace it again, cut a second one, and glue them together so I have something thick enough to work with. Next, I'll use a sanding disc on my angle grinder to do a little sculpting. The goal is to make it both stylish and comfortable. I'll finish it with some hand sanding. Once I'm satisfied with the look and feel, I'll wire it in by first drilling a narrow hole in the bottom of the handle, and then a wider hole for that push-button trigger. Once the two holes connect, I can pull the cable through, solder it firmly onto the button, and then, you guessed it, I'll hot glue the button into place. Look at that! Now I have a perfectly nice little thing. Time to ruin it by cutting the top clean off. I clean up the cut edges with some more 150 grit, and I want to carve a groove down the center on both sides. This will hold the injector shaft. Next, I'll make a closure mechanism. There are a few ways I've experimented with doing this. The first one just had a hinge on it. Another I made just used some thick rubber straps. For this build, I'm going to try just using a small hasp and some stainless steel welder wire that I've sculpted to make the hook, as well as a few carpentry staples. Now, if I'm being honest, this was easier said than done. I ended up having to do it twice and managed to start bleeding somehow at some point. But I did get it working, and I'm pleased with the result. I oil the injector up with a little linseed for good measure, and I also use a small piece of rubber weather stripping to hold the lure lock extender in place when it's clamped in. Janky? Yes. Functional? We'll see. As a finishing touch, I'll use some picture hanger hardware, some clips, and a bit of shoelace to make my strap. I'll also attach a small carabiner that I'll be using to clip the culture bag onto the strap for maximum REMIS mobility and style.
Hi, my name is Paul Lin. Before you go, I'd love to tell you a little bit about the backstory of this project and why it was important to me to make this video and share this idea in the first place. When I first began exploring these ideas, I was squatting in a shack that I built out of upcycled construction waste in my friend's backyard. I had spent years learning the ins and outs of mushroom cultivation, running experiments in the garage, waiting tables, working into the wee hours, scrimping, saving, hustling odd jobs, trying to start a small, urban, underground, one-man band, organic mushroom cultivation operation, growing oyster mushrooms and the like to sell to restaurants and at the local farmers market. At last, I'd finished building my lab, I had several solid runs under my belt in my new production space, and I quit my day job and went full-time critter. I was ramping up to my full weekly production goal of about 100 pounds of mushrooms, and there was a busy and promising tourist season on the horizon. The year was 2020. I ended up composting thousands of dollars worth of gourmet mushrooms, and like many of us, I tightened my belt and I went back to the drawing board. I've heard some say that necessity is the mother of invention. I would have to guess then that the father is desperation. In the whole mushroom cultivation process, the part I was most excited about was the liquid fermentation stage. I believed then, as I do now, that liquid culture is the future of mushroom cultivation. It was around the same time that I first had the idea of using medical IV bags to transport, store, and dispense liquid culture, and started using peristaltic pumps in the lab with the intention of developing some kind of dispensing system. Little did I know that the seeds of REMIS had already been planted. Before I knew it, I was selling enough of these bulk liquid culture bags through my various wholesale accounts that I needed to figure out a more efficient way to scale my production process. On their own, none of these individual innovations were really all that new, but I realized that together as a system, I had an idea that was unique enough to be patentable. So I started researching intellectual property law, and I authored 2 utility patent applications, complete with drawings, specifications, one for REMIS and one for my battery-powered laminar flow hood idea. And I even went as far as spending my last savings hiring an intellectual property attorney to do a professional patent search and assure that the applications that I had authored would actually pass muster at the patent office. I got as far as finally filing provisional patent applications, which is a sort of intermediary step that's designed to help inventors get ideas to market without having to cough up the tens of thousands of dollars that it costs on average to file a full-on non-provisional utility patent. Now at that time, REMIS still had some kinks to work out, so I figured I would start with the laminar flow hood. I built several prototypes, established some relationships with parts manufacturers, and then I launched a Kickstarter campaign to try to crowdfund the development of the product. The whole thing was a bust. I just didn't have the reach. I did have a few takers at least and built a few flow hoods, but it was nowhere near the amount of money I'd already sunk into the project, and certainly not what I needed if I was going to be able to move forward with it. But more than that, I started to realize that patents, like copyrights and other forms of intellectual property protection, are really pretty useless if you don't have the means and the wherewithal to actually enforce them. Here I was, practically homeless, steeped in student debt and counterculture ideology. Was I really gonna muster the legal resources to litigate patent infringement? On top of it all, I started to realize what building an enterprise of this type actually entails. In order to produce a quality product at a competitive price, I would need to bust my butt for peanuts building the damn things myself every day, or I'd need to offshore manufacturing where labor is cheap and pretend that I'd never heard of things like shipbreaking. If I were lucky, I might just rise to the level of success and status of such enterprising capitalists as those whose tutelage I'd sought so long and hard to escape. But I wasn't so sure that I would make it that far without losing something even more precious in the process. The whole thing was untenable. Even if I somehow managed to succeed in big business and somehow retain my human soul, I had no doubt that sooner or later my beloved REMIS would eventually fall at the hands of the dreaded Romulus, the ruthless oligarch monopoly undermining luminary underdog's success. So it was that I decided to heed the counsel of my dearest teacher and our good old Uncle Hank, who said, "As long as possible, live free and uncommitted." Instead, I chose to continue being poor but creative, and promised myself that someday I would honor the aspirations of these ideas by creating some detailed how-to videos, so that anyone and everyone who's interested and could benefit from these ideas can have free and open access to them. Not patenting them to keep them exclusive and proprietary, but rather unpatenting them, to make them free and accessible to all. No one can steal that which is freely given. This is the spirit of open source mycology. Thanks for joining me for part of this journey. I hope that you'll test, improve, and share these ideas, and help REMIS soar to new heights. And of course, don't forget to subscribe and stay tuned for lots more upcoming educational videos in the spirit of my life dream of a free school. My friends, we live in a time when, as much as ever, we need creative, collaborative solutions to systemic problems. Technical innovation alone will not lead us out of the dark night of the legacy of human industry. We need collaboration, free exchange of ideas, and we need deference to a more than human perspective. Above all, we need unity in our collective quest to secure a viable future for our shared world, for our children. Fungi are the vanguard at the front lines of the global environmental struggle, but they can't do it alone. They need our help. Only together may we fulfill our calling as the heads, the hands, and the hearts of this decentralized planetary intelligence we know lovingly as Fungaia.
Is your mycelium running? Then you'd better go catch it!